You're recording this?
Yep.
Can you hear me right now?
Yep, it's on there. Yep. Trevor's the
What
start of
if I
the
cuss,
video.
then you'll have to edit it like
Nope, I'm going to leave it, and I'm going to send it to your dad, and I'm going to say, look at what we did in class today. I just wanted to show you. That's all right.
Alexis and Mitch are watching this now.
Yep, exactly. Okay, so chapter 23 now. We're going to talk about confidence intervals for a population mean. So mu is the true population. That's the true mean. The true mean. And what is the sample mean? What do we use to represent the sample mean? X. Yep, you were right. X bar. Okay, the sample mean is X bar. So, in addition to using interval estimates for population proportions, P, we can also use confidence intervals to estimate the true value of a population mean, mu. The formula for a confidence interval for a population mean is based on the sampling distribution of the sample mean X bar. So this is a review. So recall that from the last chapter, 18. The mean of X bar is the true mean, and the standard deviation of the sampling distribution of the sample mean is sigma divided by the square root of n. And it's approximately normal when n is greater than 30. So this falls, this is necessary when we're checking the conditions. When we're dealing with a population mean, our conditions are random sample from population of interest, less than 10% of the population, that being independents, and third is the greater than 30, large sample size. When it was proportion, it was the n times p and n times q greater than 10. So you do have to keep those straight. That means reading enough, practicing enough that you can keep those conditions straight in your head. So thus far we've been using critical z-values from the normal distribution to make our confidence intervals. Hold on, sorry. So, we've been using critical z-values. So critical z-values, we've got the mean in the center, okay, or the true proportion in the center. And then how many standard deviations away do we typically, what's the most common confidence interval? 95%, which is allowing us 2 standard deviations away, so 95%. And what's the critical z-score for that? 1.96, so 1.96. Basically this here is negative 1.96, that's the z-score here, and this is positive 1.96. We're allowing ourselves to go above and below the mean by about 2 standard deviations. A z-score, the definition of a z-score is the number of standard deviations from the mean. Alright, so this is what we've been using so far. But we cannot use this anymore. Well, we can use it when we do proportions, but we cannot use it for the mean. So, and here's why. So that a z-score is calculated this way: the observed value minus the expected value divided by the standard deviation. X bar minus mu over the standard deviation. Okay, whatever the standard deviation is that you need to find for your thing. As long as x is normally distributed, the distribution of z will also be normal. Okay? If the sample mean is normal, z will be normal. This is because z is a linear transformation of x bar. In other words, mu, sigma, and n are all constants, and the shape shouldn't change, only the center and spread. So what we're leading up to here, this is just kind of an explanation of why we cannot use the z-scores anymore. Why we are not allowed to have a critical z-value in our confidence interval for a mean. So we're just leading up to the why and what we do about it. So, however, we rarely, if ever, know sigma, the population standard deviation. So in this formula up here, we don't know the standard deviation and we don't know the true mean. So there's where our big problem comes in. We don't know, there are 2 missing values, the mean and the standard deviation. Whereas with the proportion, the population proportion, the p, we could find the standard deviation by using the p hat and the q hat over n. We didn't have a problem finding the standard deviation for a proportion, sample proportion. But we do here because we don't know the true, there's two missing variables. All right. So, however, we rarely, if ever, know sigma, the population standard deviation. If we don't know sigma and we use S, the sample standard deviation, to estimate sigma, this distribution is not quite normal. So this is from experience by statisticians. Okay, they collected samples, and well, why can't we just use the sample standard deviation? Because that's what we did in the population proportion. We used the samples. Why can't we just use that? When they did that repeatedly, they saw that it wasn't a normal distribution. Okay, it wasn't normal. So we can't use a normal distribution. So even if the mean, the sample mean, is approximately normal. So we create a new quantity. So we give this name a new quantity. Basically, we know it's not normal. We're doing the calculation of the z-score, okay, the z-score. X bar minus the true mean divided by the sample standard deviation divided by the square root of n. This is just finding the standard deviation using the sample rather than the true value. So we call that t because it's not normal. It's not the z distribution anymore. But it's a very similar calculation. Observed minus expected over standard deviation. X minus mu over the standard deviation. All right, since t is based on two variables, the sample standard deviation and the mean, instead of just x bar like z is, the sampling distribution of t has more variability and a slightly different shape than the sampling distribution of z. However, as the sample size increases, in other words, as n gets larger, as n goes up, S gets closer to sigma, and the t distribution gets closer to the standard normal distribution. Okay, t curves are very similar to the normal curves, except that they are wider, heavy-tailed, and defined by a number called the degrees of freedom. Degrees of freedom. And this is going to become important. The degrees of freedom is abbreviated DF. The degrees of freedom is abbreviated DF, and DF is also always equal, not always, it is equal to, in confidence intervals, the number of observations, the sample size, minus 1. And that's for this chapter. Sometimes it's n minus 2. Okay, it depends. And later I'll explain more about degrees of freedom. So, all right. So, properties of the t distribution. The t curve corresponding to any fixed number of degrees of freedom is bell-shaped. So, the t distribution is a lot more complicated than the z distribution because there's two variables, and it has to do with degrees of freedom. So, if you look in the back of your textbook, you've got the tables in the back, the random number tables, and then you have your z tables. Here's your z tables on these two pages. And I just want you to notice the pictures. These are the pictures of the normal curve, right? So you turn the page and now you have the t distribution. And this is just one page is the t distribution. And do you notice much difference between the picture of the t distribution and the z from the previous page? No, not much. There's really not much difference. What they mean, this curve it's slightly a wider curve, okay? So it's wider from, like, this bell part is wider, and the tails, these are the tails, they're a little higher above the x-axis. But the whole thing is, this curve actually changes for every degree of freedom. Okay, so let's say you have a sample size of 10. Okay, you have n is 10. What would be your degrees of freedom? 9. So then 9, the way you're going to look things up, see, in a confidence interval for a sample mean, instead of having a z critical value in it, it changes to a t critical value. T. So you have to look up the critical values on here. So if you have 10 in your sample and 9 degrees of freedom, you go to 9. And then along here it has, well, on the bottom is the most useful. The bottom has the confidence interval percents, the confidence levels. The top we won't use until later on when we're doing testing and p-values. So you only pay attention to the bottom. So if I wanted the critical T for a sample size 10, okay, I'd go 9 degrees of freedom, and then I'd go and say, well, let's say I want 95% confidence, I find where they meet. That would be the critical T value that goes in front of your standard deviation. So we're going to be looking values up on here. All right, so back to what our properties of the t-distribution are. The t-curve corresponding to any fixed number of degrees of freedom is bell-shaped, symmetric, and centered at 0. Okay? Each t-curve is more spread out than the z-curve. More spread out. So here's the normal curve, and then what it means is this one, it's just wider. It's just like above it a little bit. Okay? As the degrees of freedom increase, the spread of the corresponding curve decreases. So the more you have in your sample size, this will shrink down and start looking more like a normal curve. Not that you ever have to graph it. I mean, you're gonna, if you ever draw a t-distribution, you're gonna draw it like a normal curve. Okay? But when you write confidence intervals, you don't draw the distributions. You only do that in probabilities. As the number of degrees of freedom increases, the t-curve gets closer and closer to the z-curve, the normal curve. The z-curve is the normal curve. All right, so since the t-curves are wider than the z-curve, we must go further out than 1.96 standard deviations to capture 95% of the observations. So that just means our t-values are going to be different. So to find out how far, we use a critical t-value from the table, or there's a command on your calculator called inverse t. I'll show you both. Okay, you will get a t-distribution on the AP test. You will get all the tables in the back of your book on the test. So if you want to use those or your calculator. So if the degrees of freedom is 20 and you want a 95% confidence interval, what t critical value should you use? So t will be, I can do this two ways. My degrees of freedom is 20. So I'm going to go to my book and I'm going to say, well, that's if it says degrees of freedom is 20. So I go to 20, and then I go to 0.95, was it 95? Okay, and I see where they meet, and that's 2.086. So that's 2.086 from the table, but how do I do it on my calculator? So I go to inverse t, second distribution. What do you see right below inverse norm? Inverse t. Okay, so now we need to think exactly the same way we did before. We can't just type in 0.95. Okay, the command in inverse t and inverse norm is area to the left. Area to the left. Well, whenever you're doing a confidence interval, you're dealing with the middle percent. So what we're dealing with here is the middle 95%. So what percent is up here? 2.5%. So what percent is down here? 97.5 is everything down below that. Yes.
Is there anywhere else I can do that? Because my calculator doesn't have it.
It doesn't have, you have a table. That's the other way you can do it.
All right.
So inverse t, and so 97.5 is 0.975. And then after that, you have to tell it comma, you have to tell it the degrees of freedom. So the inverse t command, after it, you have to tell it your area to the left of the upper end of your confidence interval, and comma the degrees of freedom. So you have to tell it that you have 20 degrees of freedom. Now if you hit enter, it's thinking, and it gave me t equals 2.086. It gave me the same thing the table did. And occasionally they'll be slightly different. And maybe after 4 decimal places. Okay, so now it says, thus to capture the middle 95% of the t-distribution with 20 degrees of freedom, you must go out 2.086 standard errors. So it's a little bit, you have to go out further than 2 standard deviations to capture 95% of the data in a t-distribution. So find the t-critical values for the following. So I'm going to let you give this a try. I'm going to give you 5 minutes using what we just did, and then we've got a couple confidence intervals to write.